What if the universe could end in the blink of an eye, not with a bang, not with a whimper, but with a silent, invisible wave rewriting reality itself? Picture this, a single quantum event, smaller than an atom, triggering a chain reaction that spreads at the speed of light, unraveling the very fabric of space and time. No explosions, no dramatic collapse, just the quiet, unstoppable transformation of everything we know into something unrecognizable. This isn't science fiction. It's a genuine possibility lurking in the equations of modern physics, a phenomenon known as vacuum decay, and if it's real, it could erase the universe without warning, leaving no trace behind. The idea that our universe might be sitting on the edge of destruction sounds like something from a cosmic horror story, but it's rooted in the laws of quantum mechanics and the nature of the vacuum itself. You might think of empty space as just nothingness, but in reality, it's a seething, bubbling sea of potential energy held in a delicate balance. What if that balance were to tip? What if somewhere in the vast expanse of the cosmos, a tiny fluctuation pushed space over the edge, creating a new, more stable state of reality, one where the laws of physics as we know them no longer apply? The terrifying truth is, once this process begins, there's no stopping it. Like a domino effect on a cosmic scale, the change would spread outward, rewriting the universe in its wake. But how real is this threat? Could it happen tomorrow, or is it just a fascinating thought experiment? Today, we're diving deep into one of the most unsettling theories in modern physics, one that challenges our understanding of existence itself. We'll explore how vacuum decay could start, what it would mean for the fate of the cosmos, and why some scientists take it seriously. From the bizarre world of quantum fields to the ultimate fate of spacetime, this journey will take us to the edge of what we know and beyond. So buckle up. By the end of this video, you'll never look at the universe the same way again. To understand vacuum decay, we first need to rethink what nothingness really means. The quantum vacuum isn't empty, it's a simmering ocean of energy fields, constantly fluctuating even in what we perceive as empty space. Think of it like a calm lake that's actually teeming with invisible currents beneath its surface. These fields exist in what physicists call a false vacuum state, seemingly stable, but potentially just one quantum nudge away from collapsing into a more stable configuration. Here's where things get unsettling. If even a single point in space were to transition to this true vacuum state, it would act like a cosmic spark. The change wouldn't just stay put, it would spread outward in an expanding sphere at the speed of light, rewriting the laws of physics as it goes. Picture dropping a single drop of ink into a glass of water, watching it spread until every last molecule is transformed. Except in this case, the ink is a new set of physical constants where atoms might not hold together, where light might not travel the same way, where the very building blocks of reality could become unrecognizable. What makes this scenario uniquely terrifying is its inevitability once triggered. Unlike asteroid impacts or supernova, which we might theoretically detect and prepare for, vacuum decay would give no warning. By the time the wave reached us, it would already be too late. The moment the bubble touches Earth, the universe we know would cease to exist in that spot, instantly and irreversibly. No explosion, no sound, just silent, instantaneous transformation. Scientists describe this as the ultimate cosmic catastrophe because it wouldn't just destroy life, it would rewrite the rulebook of existence itself. The constants that allow stars to shine, particles to bind, and consciousness to emerge could all vanish in favor of new, alien physics where none of those things are possible. It's not death in the traditional sense, it's the erasure of the very conditions that make life conceivable. Yet for all its apocalyptic potential, vacuum decay remains theoretical. The mathematics suggest it's possible, but we have no evidence it's ever occurred in our universe's history. That uncertainty is part of what makes it so fascinating and so unsettling. We're left staring into the quantum abyss, wondering if the universe is fundamentally stable, or if somewhere in the infinite reaches of spacetime, a single quantum flicker might already be rewriting our future. Imagine the universe as a vast cosmic mountain range, with valleys representing different possible states of reality. Right now, we're sitting in one particular valley, what physicists call the false vacuum. It's stable enough that we've built galaxies, stars, and civilizations here, but here's the catch. This valley isn't at the very bottom. Somewhere out there, hidden in the quantum landscape, lies a deeper valley, the true vacuum state. And the terrifying possibility is that our universe could suddenly roll downhill into it. The difference between these two states comes down to energy. The false vacuum is like a ball perched on a ledge. It seems stable for now, but given the right nudge, it could come crashing down. In quantum terms, this ledge represents higher energy levels that allow for the physics we know: electromagnetism, gravity, the strong and weak nuclear forces. But the true vacuum would represent the lowest possible energy state, where those fundamental forces might behave completely differently. Atoms might not form. Light might not exist as we know it. The very rules that govern reality could be rewritten in an instant. What makes this more than just theoretical is how phase transitions work in nature. We see this play out all around us: water turning to ice, metals becoming superconductors at low temperatures. Each transition reshapes matter at a fundamental level. Now apply that concept to spacetime itself. If any tiny region of the universe underwent this vacuum phase transition, it wouldn't just change locally. Like a spark in dry grass, the new ground state would spread outward at light speed, creating an expanding bubble of alien physics where our familiar laws no longer apply. Interestingly, this isn't just wild speculation, it's grounded in solid physics. The Higgs field, which gives particles their mass, exists in such a false vacuum state according to our best measurements. Calculations suggest it's stable, probably, but probably isn't exactly comforting when we're talking about universal annihilation. Some theories even suggest that vacuum decay might have already happened elsewhere in the cosmos, with those bubbles of new physics racing toward us right now. We wouldn't know until they arrived. There's no advance warning when the change propagates at light speed. Yet for all its destructive potential, vacuum decay also reveals something profound about our universe. The fact that we exist at all suggests our cosmic valley has remained stable for billions of years. That stability allowed stars to ignite, planets to form, and life to emerge. But it also means we're living on borrowed time in a sense, existing in what might ultimately be a temporary configuration of reality. Every second that passes without vacuum decay is both a statistical miracle and a reminder of how little we truly understand about the fundamental nature of existence. The Higgs field isn't just another piece of the cosmic puzzle, it's the invisible architect shaping the very structure of our reality. This quantum field permeates all of space, interacting with particles to give them mass like thick syrup, slowing down objects moving through it. Without this effect, electrons would zip away at light speed, atoms could never form, and the universe as we know it would be impossible. But here's the twist: this fundamental force might be holding the universe together by the thinnest of threads. Current experiments at the Large Hadron Collider reveal something startling. The Higgs field appears to exist in a state physicists call metastable. Imagine balancing a pencil perfectly on its tip. Technically, it's standing upright, but the slightest vibration could send it tumbling. That's essentially our universe's predicament. The energy state of the Higgs field isn't at the absolute lowest possible level. It's perched on a quantum ledge, stable for now, but potentially one fluctuation away from cascading into a more fundamental configuration. What would happen if that transition occurred? The consequences are almost beyond comprehension. As the Higgs field shifted to a lower energy state, the rules governing particle masses would rewrite themselves in real time. Protons might suddenly weigh twice as much or lose their mass entirely. Atomic nuclei could disintegrate as the strong nuclear force becomes unmoored. Even the electrons orbiting atoms might vanish like smoke in the wind, transforming solid matter into an unrecognizable quantum soup, the most unsettling part. This transition wouldn't happen gradually. Quantum tunneling means the change could occur instantaneously at any point in space, creating an expanding sphere of annihilation where physics itself mutates. One moment you're drinking coffee, the next moment the cup in your hand and the atoms composing your body no longer behave by the same rules that allowed them to exist in the first place. Yet there's a fascinating contradiction at play here. The same measurements suggesting potential instability also indicate this metastable state could last longer than the current age of the universe. The Higgs field has maintained this delicate balance for over 13 billion years. Why would it collapse now? Some theorists argue we might be safer than the math suggests, with unknown quantum effects stabilizing our cosmic predicament. Others point out that in an infinite universe with infinite time, even the most improbable events eventually occur. This scientific detective story continues unfolding in particle colliders around the world. Every proton smash at the Large Hadron Collider provides new data about the Higgs boson's precise properties, tiny clues that could either reassure us about cosmic stability or reveal we're living on borrowed time. For now, the universe continues its silent balancing act, with every second of continued existence simultaneously a triumph of stability and a reminder of how little we truly control. Quantum tunneling sounds like something from science fiction, particles magically passing through barriers they shouldn't be able to cross. But it's a very real phenomenon that could hold the key to the universe's undoing. Picture a ball rolling up a hill, only to suddenly appear on the other side without ever reaching the top. That's essentially what happens at the quantum level, where particles don't follow the neat, predictable paths of classical physics. Instead, they operate on probability, occasionally tunneling through energy barriers that should be impossible to overcome. Now imagine that same principle applied not to a single particle, but to the fabric of space-time itself. This is where vacuum decay enters the picture. Our universe's metastable state is like a ball resting in a shallow valley, with towering energy hills separating it from a deeper, more stable valley. Classically, the ball should stay put forever, but quantum mechanics introduces a terrifying loophole given enough time. There's a tiny but real chance the ball could tunnel through those hills and come rolling down into the lower valley. Translated to cosmology, that means a random quantum fluctuation could punch through the energy barrier, keeping our false vacuum stable, creating a microscopic bubble of true vacuum. And once that bubble forms, the rules change forever. The numbers involved are mind-bending. For a single proton-sized region of space, the odds of this happening might be once in a trillion years. But here's the catch: the universe is unimaginably vast and old. With an infinite number of quantum events occurring across an infinite expanse of space-time, even the most improbable events become inevitable. Somewhere, in some distant galaxy, or perhaps right next door in cosmological terms, that one in a googolplex chance might already have occurred. What makes this scenario uniquely unsettling is the asymmetry of destruction. The bubble would grow at light speed, but we'd have no warning. Unlike a supernova or gamma-ray burst, which sends detectable radiation ahead of it, vacuum decay doesn't broadcast its arrival. The leading edge of the bubble is the change itself. One moment, physics works as normal. The next, everything inside the bubble's radius operates under alien rules where matter as we know it can't exist. Some theorists argue this might have already happened countless times in distant regions of the cosmos, with expanding bubbles of new physics racing through the void. Others suggest our universe's longevity is evidence that such events are rarer than calculations predict. But in the grand calculus of cosmic time, rare doesn't mean impossible. It just means we've been lucky so far. Every second that passes without vacuum decay is another roll of the quantum dice, another moment where the universe's precarious balance holds it for now. The speed of light isn't just a cosmic speed limit. It's the terrifying velocity at which our universe could unravel if vacuum decay began. Picture standing on a beach as an invisible tsunami races toward shore at 670 million miles per hour. You wouldn't see the wave coming because its leading edge travels precisely as fast as the light that would warn you of its approach. By the time your eyes could register the disaster, it would already have rewritten the physics of your retinas, your brain, and the world around you. This is the chilling reality of vacuum decay's expansion, a boundary where the old universe ends and the new one begins, advancing relentlessly at light speed with no possibility of evasion or escape. What makes this scenario so uniquely horrifying is its absolute inevitability once initiated. Most cosmic catastrophes, asteroid impacts, nearby supernova, at least offer some window for detection or reaction. But vacuum decay's expanding sphere of transformation carries its own destruction within it. The moment a point in space transitions to the true vacuum state, that change propagates outward in all directions like a shockwave through the quantum fields that underpin reality. There's no material barrier that could stop it, no distance great enough to flee. Even if we detected the event occurring in a galaxy billions of light years away, the lethal bubble would already be halfway here by the time its light reached our telescopes. Consider the implications for our cosmic neighborhood. If vacuum decay began near the center of our Milky Way, approximately 25,000 light years away, we'd have millennia of false security before the end arrived. But if it sparked just 1 light year away, perhaps triggered by some exotic particle collision in interstellar space, we'd have less than 12 months before the wave reached Earth. And in the grimmest scenario, if it began within our solar system, the entire planet would transition to the new vacuum state within seconds. The difference between these outcomes hinges entirely on where the quantum dice happen to fall, with no possible early warning system to alert us. This light-speed propagation reveals a profound truth about the nature of reality itself. In our daily lives, we're accustomed to threats that give some observable indication of their approach: sound waves from an oncoming storm, seismic tremors before an earthquake. But vacuum decay operates on a more fundamental level, altering the very medium through which such signals travel. It's not moving through space so much as rewriting space itself, leaving no unaffected region ahead of it to broadcast a warning. The first sign of trouble would be the universe around you suddenly operating under alien physical laws, assuming you still existed to perceive it. Theoretical models suggest that within the bubble's interior, the transition would be instantaneous and total. Atoms might lose their binding forces, dissolving into quark-gluon plasma. Electromagnetic radiation could propagate differently, making light itself behave in unrecognizable ways. Even time might flow under new rules if it exists at all in the true vacuum state. This isn't merely the destruction of matter, it's the erasure of the operating system that allows matter to exist in its current form. A chilling thought experiment suggests that conscious observers inside the bubble might not even recognize their own dissolution, as the physical processes enabling thought and perception would cease functioning as before. Yet amid this existential dread lies a strange comfort in the physics. The very fact that vacuum decay spreads at light speed, not faster, means it obeys Einstein's cosmic rulebook. Even the end of reality plays by the universe's established laws. This consistency offers scientists crucial clues about how to detect potential vacuum metastability through subtle measurements of the Higgs field. While we can't stop the wave once it starts, understanding its mechanics helps us assess whether our cosmic valley is truly precarious or more stable than initial calculations suggest. For now, the night sky remains reassuringly familiar, but every photon arriving from distant galaxies carries silent testimony that the laws of physics still hold, at least for this moment in cosmic history. Could humanity accidentally become the architect of its own cosmic demise? The unsettling possibility that our scientific curiosity might trigger vacuum decay has haunted the edges of physics discussions for decades. Picture a scenario where particle collisions in underground laboratories designed to unravel the mysteries of the universe inadvertently create the precise conditions to destabilize spacetime itself. It sounds like the plot of a dystopian sci-fi novel, but some theoretical models suggest it's not entirely impossible. The mathematics reveal why this fear persists. When protons slam together at nearly light speed inside machines like the Large Hadron Collider, they momentarily recreate energy conditions not seen since the universe's first trillionth of a second. In these microscopic fireballs, the Higgs field, that invisible architect of mass, could theoretically be jolted out of its metastable state. The resulting quantum domino effect might spawn a bubble of true vacuum that expands uncontrollably. The odds are astronomically low, but in the realm of quantum probabilities, unlikely doesn't mean never. Yet here's the crucial perspective often lost in sensational headlines. Nature's particle accelerators dwarf anything humans could build. Cosmic rays, high-energy particles from deep space, routinely collide with Earth's atmosphere at energies millions of times greater than anything produced in our labs. If these natural collisions haven't triggered vacuum decay over billions of years, human experiments almost certainly won't. The universe has been stress testing itself since the Big Bang with far more violent experiments than we could ever devise. Still, the debate raises profound questions about scientific responsibility. Some theorists argue we should weigh even infinitesimal risks against potential rewards when probing fundamental physics. Others counter that withholding exploration due to remote theoretical dangers would paralyze progress. After all, every major discovery, from electricity to nuclear energy, carried unforeseen risks initially. The key difference: vacuum decay wouldn't just threaten a city or civilization, it could erase the cosmic playing field itself. This tension between curiosity and caution reflects a deeper truth about our place in the universe. We're cosmic newcomers tinkering with forces we barely understand, like children playing with a mysterious control panel buried in the sand. Each experiment advances our knowledge, but also reminds us how fragile reality's equilibrium might be. For now, the consensus remains clear. The benefits of particle physics far outweigh hypothetical risks. But as colliders grow more powerful and probes delve deeper into quantum frontiers, this ethical balancing act will only become more nuanced, a reminder that knowledge and existential risk sometimes share the same laboratory. While human experiments pose negligible risks, the universe itself constantly runs the ultimate high-stakes physics experiment, cosmic rays. These high-energy particles, accelerated to nearly light speed by distant supernova and black holes, streak through space with energies that make our largest particle colliders seem like toys. Each second, thousands of these subatomic bullets pierce Earth's atmosphere, some carrying millions of times more energy than anything humans can produce. Among this relentless cosmic barrage might lurk the ultimate trigger for vacuum decay, a single particle with just the right properties to nudge quantum fields past their tipping point. The mechanism is chillingly straightforward. When an ultra-high-energy cosmic ray slams into Earth's atmosphere, or any patch of interstellar space, it creates a microscopic fireball of extreme conditions. For an instant, temperatures and energies rival those moments after the Big Bang. Within this fleeting inferno, quantum fields could theoretically be pushed into unstable configurations, like a needle briefly puncturing the delicate membrane separating our false vacuum from oblivion. Most of the time, the fields snap back unharmed, but given enough attempts across enough of space-time, the statistical dice might eventually land on catastrophe. What makes this possibility so unsettling is its sheer ubiquity. Unlike hypothetical lab accidents that could be regulated or stopped, cosmic rays are an inescapable natural phenomenon. They've been bombarding the universe since the first stars ignited, meaning the experiment has been running for over 13 billion years without, as far as we know, triggering vacuum decay. This offers some mathematical comfort. If it hasn't happened yet despite quintillions of high-energy collisions across the cosmos, the odds must be astronomically low. Yet probability behaves strangely on cosmic scales. A 1 in a trillion chance might seem reassuring until you realize the universe performs trillions of such experiments every second. Some theories even suggest vacuum decay might require a cosmic ray of absurdly specific energy, not too high, not too low, making the event rarer still. Others propose that certain regions of space with stronger magnetic fields or denser quantum vacuum fluctuations could act as cosmic catalysts, increasing the risk in select areas of the galaxy. The deeper we look, the more we realize how little we truly understand about these high-energy processes. Modern detectors like the Pierre-Auger Observatory have mapped cosmic rays with energies exceeding 100 quintillion electron volts, so powerful they shouldn't exist under current astrophysical models. These "oh my god" particles, as physicists call them, defy expectations about how nature can accelerate matter. If such extreme phenomena can occur naturally, what other quantum surprises might lurk in the cosmic background? Perhaps the greatest irony lies in our detection methods. When scientists monitor cosmic rays using vast arrays of sensors, they're effectively watching for sparks that could, in some alternate reality, ignite universal annihilation. Yet these same observations provide our best evidence that vacuum decay remains theoretical. Every cosmic ray that passes without ending reality is another data point suggesting the Higgs field's ledge might be wider than we feared. Still, as detectors grow more sensitive and probe ever higher energies, each new measurement sharpens our understanding of how close or how far we truly are from the quantum precipice. The Boltzmann brain paradox twists our understanding of reality into a cosmic hall of mirrors. Imagine floating alone in infinite darkness, just a disembodied brain spontaneously formed from quantum fluctuations, complete with false memories of a universe that never existed. This bizarre thought experiment emerges from the same physics that makes vacuum decay possible, revealing how deeply strange our universe becomes when you follow the math to its logical extremes. At its core, the paradox asks why we find ourselves in an ordered, 13 billion-year-old cosmos, rather than as momentary aberrations in an endless sea of chaos. Given enough time, and the universe has infinite time, random particle arrangements should eventually produce self-aware structures by pure chance. These Boltzmann brains would outnumber ordinary observers like ourselves by unimaginable margins, making our existence statistically absurd. Yet here we are, surrounded by consistent physical laws and historical evidence stretching back to the Big Bang. This ties directly to vacuum decay's existential stakes. If the universe were truly unstable, why hasn't it already collapsed? One unsettling answer: maybe it has countless times, and we're simply in the fleeting calm between catastrophes. Like survivors on the last unburned patch of a forest fire, our continued existence might not prove the forest is safe, just that the flames haven't reached us yet. The longer the universe persists without decay, the more puzzling it becomes. Either we're miraculously early in cosmic history, or some hidden mechanism protects our false vacuum from quantum roulette. The paradox deepens when we consider consciousness itself. If random fluctuations can create minds from nothing, how can we trust any observation about reality's stability? Your memory of reading this sentence right now could be a Boltzmann brain's fleeting hallucination. Scientists counter that stable, coherent universes like ours are vastly more probable as lasting structures than as temporary glitches. But vastly more probable still feels shaky when dealing with infinity. What saves us from total existential vertigo is the intricate web of evidence supporting our universe's consistency. From the cosmic microwave background to fossil records, multiple independent lines of observation converge on a single, coherent history. A Boltzmann brain wouldn't have this luxury. Its reality would be riddled with contradictions. Similarly, vacuum decay's absence over billions of years suggests either incredible luck or undiscovered physics favoring stability. This philosophical quagmire ultimately highlights how little we understand about consciousness, quantum fields, and time's true nature. The very fact that we can contemplate our potential unreality might be the strongest argument that we're part of something real. Or perhaps that's just what a Boltzmann brain would rationalize before winking out of existence. The universe keeps its deepest secrets close, leaving us to wonder whether we're foundational observers or statistical flukes in an uncaring void. Eternal inflation theory rewrites the cosmic rulebook entirely. Instead of one universe with a single fate, it proposes an endlessly bubbling sea of realities, each born from quantum fluctuations in an inflating spacetime foam. Picture a boiling pot of water where every rising bubble represents an entire universe with its own unique physics. Some bubbles pop immediately, collapsing back into the quantum soup. Others expand and stabilize, creating long-lived cosmic islands like our own. In this dizzying landscape, vacuum decay isn't just a threat. It's part of the multiverse's natural life cycle, constantly pruning unstable realities while allowing robust ones to flourish. This changes everything about how we view our universe's precarious position. If eternal inflation is correct, then our cosmic neighborhood might be surrounded by failed universes that succumbed to vacuum decay long ago. Their remnants would linger as ghostly boundary walls in the greater multiverse, invisible tombstones, marking where physics once worked differently before collapsing into new states. The chilling implication: our universe's apparent stability could simply mean we're living in the calm before the quantum storm, like settlers building cities on a dormant volcano, unaware it's overdue for eruption. The numbers become even more humbling when considering cosmic Darwinism on a multiversal scale. For every universe like ours that persists billions of years, there could be countless others that flared briefly into existence only to vanish when their vacuum states collapsed. Some may have hosted alien forms of matter and energy. We can't begin to imagine entire cosmic histories erased when their fundamental constants shifted. Others might have been stillborn, dissolving back into the quantum foam before their first stars could ignite. Our existence in a long-lived universe might say less about specialness and more about survivorship bias. We can only observe physics that permits observers to exist. Remarkably, this framework offers potential solutions to cosmology's deepest puzzles. The finely tuned constants of our universe, gravity's strength, the mass of electrons, the cosmological constant might not be miraculous coincidences but inevitable outcomes of multiversal selection. Universes where these values allowed complexity to emerge would be the ones lasting long enough to host life. The others, they'd be cosmic dead ends, their physics too unstable or inhospitable to persist. In this light, vacuum decay isn't just destruction, it's the multiverse's quality control mechanism, filtering out non-viable realities. Yet for all its explanatory power, eternal inflation raises troubling questions about predictability. If every possible universe emerges somewhere in the multiverse, how can we ever test which physical laws are fundamental versus local accidents of our cosmic bubble? Some theorists argue that certain signatures in the cosmic microwave background, anomalous cold spots or polarization patterns, might reveal collisions with other bubble universes. Others suggest that the Higgs field's precise metastability hints at selection pressures from this greater multiversal environment, but concrete evidence remains elusive, leaving us straddling the line between profound theory and speculative metaphysics. What emerges from this grand perspective is a universe far stranger and more dynamic than we ever imagined, not as a solitary cosmic accident, but as one thread in an infinite tapestry of realities. Our physics becomes provincial, our cosmology local. The grand questions shift from why do these laws exist to why have these laws persisted? In this multiversal ecosystem, vacuum decay transforms from an existential threat into part of nature's rhythm, the shadow that makes the light of our temporary stability all the more remarkable. Every second our universe continues becomes statistically more extraordinary, another moment where our particular configuration of quantum fields holds firm against the entropic pull of the multiverse. Whether this vision represents profound truth or elegant fiction remains unknown, but it underscores a humbling reality. The ground beneath our feet, both literally and cosmically, may be far less solid than it appears. As we peer deeper into quantum fields and cosmic backgrounds, we're not just studying our universe's rules, but potentially uncovering the hidden pressures that shaped those rules across an unfathomably larger reality. The silence of the night sky takes on new meaning not as emptiness, but as either the calm of cosmic isolation or the quiet before a transformation we cannot yet see coming. The terrifying truth about vacuum decay is its perfect stealth, a cosmic assassin moving at light speed, leaving no trace until the blade falls. Unlike supernova that paint the sky with radiation or black holes that warp spacetime visibly, this phenomenon offers zero warning signs. Quantum fields governing our reality could already be unraveling in some distant galaxy, sending silent shockwaves our way, with no conceivable method to detect their approach. Some physicists have played with the idea that subtle quantum irregularities might serve as early tremors, perhaps particles behaving oddly or energy levels fluctuating in unexpected ways. These could theoretically hint that the Higgs field is becoming unstable, like microscopic cracks forming in the foundation of reality. But so far, every particle collision, every astronomical observation, every precision measurement of fundamental constants shows no deviation from expected behavior. The universe operates with eerie consistency, giving no indication that its stability is anything but absolute. This absence of evidence cuts both ways. On one hand, it's reassuring the longer we go without seeing anomalies, the more likely our vacuum state is robust. on the other, it means we're flying blind. Imagine being on a ship in the fog, knowing icebergs might lurk ahead but having no sonar to detect them. That's our predicament with vacuum decay. The cosmos could be teeming with bubbles of new physics expanding toward us, and we'd have no way to know until they rewrote the rules of our existence. The only potential warning would come from observing distant regions of space undergoing sudden, inexplicable changes, galaxies winking out not from cosmic collisions but from fundamental physics breaking down. But even this is a paradox, since vacuum decay propagates at light speed. The light showing us those distant events would arrive simultaneously with the decay itself. By the time we saw a galaxy disappear, the same wave would already be upon us. This invisibility makes vacuum decay unique among existential risks. Asteroids can be tracked, supernova can be observed centuries in advance, even climate catastrophes unfold gradually enough for adaptation. But vacuum decay, it's the ultimate cosmic ambush, an enemy that moves at the speed of its own warning signal. The very laws of physics that allow us to study the universe also ensure we'd be the last to know if those laws were about to change. Yet in this uncertainty lies a strange kind of freedom. Without the ability to predict or prevent such an event, we're left to focus on what we can control, exploring, understanding, and appreciating the universe while it lasts. Every stable moment becomes a gift, every ordinary second a minor miracle. The silence of the cosmos might be unnerving, but it's also the silence that allows life to flourish for now in this fragile pocket of equilibrium. Black holes stand as the universe's ultimate fortresses, cosmic monoliths so dense that not even light can escape their grip. For billions of years, they've devoured stars, warped space-time, and defied all known laws of physics with their enigmatic singularities. Yet in the face of vacuum decay, even these gravitational Goliaths would meet their match. The rewriting of fundamental forces wouldn't just weaken black holes, it would dismantle them from the inside out, erasing the very rules that allow them to exist. Picture a black hole's event horizon, that infamous point of no return where gravity's pull becomes inescapable. This boundary doesn't exist in isolation. It's woven into the fabric of space-time itself, dependent on the precise way mass curves the universe. But if vacuum decay swept through, altering the behavior of gravity or even dissolving the Higgs field that gives particles mass, the equations governing that curvature would unravel. The event horizon wouldn't so much collapse as cease to be meaningful. Like a castle gate melting into mist, the barrier separating the black hole from the rest of the universe would vanish as physics redefined what gravity even means. The singularity at a black hole's heart, a point of infinite density where our current laws of physics break down, would face an even stranger fate. In a true vacuum state, the concepts of density and spacetime curvature might not operate as they do now. That infinitely compressed knot of matter could simply relax, as if the universe hit a cosmic reset button on extreme gravity. Some theories suggest singularities might dissipate into exotic particles. Others propose they'd unravel like a tangled thread suddenly freed from tension. The unsettling truth is we can't precisely predict their fate, because the new physics governing the true vacuum state would be as alien to us as our universe's rules would be to the inside of a singularity. This cosmic irony runs deep. Black holes spend eons consuming everything around them, only to potentially fall victim to a force they can't consume, a wave of change that doesn't interact with matter so much as redefine what matter is. Their destruction wouldn't come from some greater external power, but from the instability of the quantum fields they're built upon. Like sandcastles reliant on the very grains that compose them, black holes depend on the universe's current configuration to maintain their existence. Change that configuration and the castles crumble. the implications spiral outward. If vacuum decay can unmake black holes, what does that suggest about the fundamental nature of reality? Perhaps the structures we consider permanent galaxies, stars, even space-time itself are only temporary arrangements in a deeper, more volatile quantum landscape. The universe's apparent stability might be an illusion, a fleeting moment of equilibrium in an endless dance of field states. Black holes, often seen as the end stages of cosmic evolution, would instead become markers of a physics that was until the rules changed without notice. Yet here's the haunting counterpoint. If vacuum decay hasn't occurred yet in our observable universe, its absence might explain why black holes persist at all. Every active galactic nucleus, every quasar, every gravitational wave detection from distant collisions serves as indirect evidence that our corner of reality remains untouched by such a phase transition. The continued existence of these gravitational monsters suggests their underlying physics still holds sway for now. Each one is both a reminder of the universe's destructive power and a silent sentinel, its very presence whispering that the delicate balance of our false vacuum endures. This paradox leaves us with a profound cosmic perspective. The mightiest objects in creation are, in the end, just as vulnerable as the atoms in our bodies to the universe's deepest rules. Whether through gradual evaporation via Hawking radiation or the sudden erasure of vacuum decay, even black holes aren't eternal. Their impermanence mirrors our own, tying the fate of the cosmos's greatest giants to the same quantum uncertainties that govern everything else. In the grand scheme, nothing, not even a singularity, lasts forever. Time itself may be the silent conspirator in the universe's potential undoing. The mathematics behind vacuum decay reveal a chilling truth given an infinite timeline. Even events with infinitesimal odds become guaranteed. This isn't speculation, it's the ironclad law of probability playing out on cosmic scales. Picture rolling a die with 1 trillion sides every second for eternity. However unlikely, that die will eventually land on the one catastrophic outcome that reshapes reality. The concept known as quantum immortality takes on terrifying new dimensions when applied to the lifespan of the cosmos. Ordinarily, we think of this idea in personal terms, the notion that consciousness might persist through increasingly improbable scenarios, but expand that thinking to universal scales, and a darker picture emerges. Each passing moment without vacuum decay isn't necessarily evidence of stability. It could simply mean we're living in the shrinking window before statistical inevitability catches up with us. The universe's continued existence doesn't prove safety any more than drawing 20 aces in a row proves the deck isn't stacked. Cosmologists calculate that the metastable state of our vacuum could potentially last for 10 to the power of 100 years, a number so large it defies comprehension. Yet even this unimaginable time frame represents merely a blink in the face of eternity. Given endless time, quantum fluctuations will eventually find the perfect alignment to tip the cosmic scales. Some theories suggest this process might already be underway in distant regions of space, with expanding bubbles of new physics racing toward us at light speed. We wouldn't know until they arrived, making every second of continued existence both a statistical anomaly and a temporary reprieve. This perspective transforms our understanding of cosmic history. The 13 billion years since the Big Bang, while vast to human perception, might represent the briefest initial phase of universal stability. Like passengers boarding a ship just before its maiden voyage, we have no way of knowing whether we're at the beginning of an endless journey or nearing some invisible threshold where the odds turn against us. The unsettling implication is that the longer the universe persists, the more precarious its position becomes, not because anything fundamentally changes, but because probability's slow tide keeps rising. Yet there's a curious counterpoint hidden in these calculations. The very fact that complex life emerged relatively early in cosmic history might suggest our universe is unusually stable. If vacuum decay were imminent on cosmological timescales, the window for stars, planets, and life to form would have been vanishingly small. Our existence could therefore be indirect evidence that the metastable state will hold far longer than basic estimates predict. Or perhaps we're simply the first generation of observers in a young universe, destined to be followed by quadrillions of years of sterile emptiness before the quantum storm finally arrives. The deeper we probe this temporal paradox, the more it challenges our notions of cosmic purpose. If the universe's ultimate fate is sealed by statistics rather than physics, what does that say about the nature of reality? We're left balancing on a razor's edge between two unsettling possibilities: that we're either extraordinarily lucky to exist in the universe's brief stable period, or that some undiscovered principle protects reality from such quantum catastrophes. Both options force us to confront how little we truly understand about time's role in the grand scheme of existence. This temporal dimension adds profound weight to every astronomical observation we make. When telescopes capture light from ancient galaxies, they're not just showing us the distant past, they're providing evidence that the laws of physics held firm billions of years ago. Each photon that reaches us across cosmic epochs carries silent reassurance that vacuum decay hasn't rewritten the rules yet. But they also serve as reminders that the universe's stability can't be taken for granted. It's an ongoing phenomenon, one that could theoretically end at any point in the unfathomable future that lies ahead. The ultimate irony may be that time, the very dimension that allows complex structures like galaxies and life to emerge, also contains the seeds of their potential destruction. Like sand slipping through an hourglass, each passing moment brings the universe closer not to some predetermined end, but to the rising probability that random quantum events will eventually align in catastrophe. Whether this alignment takes a googol years or forever remains one of cosmology's most profound unanswered questions, one whose answer might be written in the quantum fields all around us, ticking away like a silent cosmic clock. Vacuum decay doesn't just threaten our universe, it shakes the very foundations of how we assign meaning to existence. If reality itself rests on a knife's edge, balanced precariously over quantum oblivion, what does that say about the significance of human achievements, memories, or even consciousness? One perspective finds unexpected beauty in this fragility. Like a sand mandala meticulously crafted only to be swept away, the ephemeral nature of everything could amplify the value of each moment. If the cosmos is borrowed rather than permanent, then every act of creation, every connection forged, becomes a quiet rebellion against the void, a way to etch meaning into the universe while it lasts. Yet this view collides with a darker interpretation. That impermanence on cosmic scales renders all striving ultimately futile. If vacuum decay could erase not just Earth, but the entire framework of physics that allows stars, planets, and life to exist anywhere, then even the grandest civilizations are little more than patterns in the sand, waiting for the tide. Some philosophers argue this realization should terrify us, while others suggest it liberates us from the weight of eternity. Without the promise of permanence, we're free to define purpose on our own terms, like travelers knowing the road ends but choosing to walk it with intention anyway. The tension between these perspectives reveals a profound truth about human nature. We're pattern-seeking creatures wired to expect continuity, yet our greatest works, art, science, love, often gain their resonance from being finite. Vacuum decay magnifies this paradox to universal proportions. forcing us to reconcile our need for lasting significance with the unsettling possibility that nothing, not even the laws of physics, is guaranteed. It's as if the universe whispered a cosmic riddle. Does meaning derive from endurance or from the intensity with which we burn against the darkness? This dilemma echoes through history in different forms. Ancient Stoics practiced memento mori, remembering death to fully appreciate life. Buddhists speak of impermanence as fundamental to existence. Now, modern physics presents a version of this wisdom written in the language of quantum fields, suggesting that the universe itself might be subject to the same transience we observe in autumn leaves or dying stars. The difference is scale. Personal mortality is one thing, the mortality of reality itself is another. Perhaps the most unsettling implication isn't that life might end, but that it might never have needed to exist in the first place. If vacuum decay proves our universe is fundamentally unstable, it raises the question of why anything emerged from the quantum foam at all. The sheer improbability of a cosmos lasting long enough for galaxies, planets, and minds to form becomes either a statistical fluke or evidence of deeper principles we don't yet understand. Some interpretations of quantum mechanics suggest conscious observers play a role in stabilizing reality, that the universe exists because we're here to perceive it. If true, vacuum decay becomes the ultimate existential irony. The act of observing our own annihilation might be what crystallizes it into being. What emerges from this philosophical labyrinth isn't despair, but a strange kind of clarity. Facing the possibility of cosmic impermanence doesn't diminish human experience, it sharpens it. Every scientific discovery, every work of art, every act of kindness becomes a beacon lit against the abyss, not because it will last forever, but because it matters now. The universe may be transient, but our ability to question, create, and connect within it remains real. In the end, vacuum decay forces us to choose. Do we see fragility as futility, or as the condition that makes every moment precious? The answer might be the most human thing of all, a defiance written not in stone, but in the fleeting patterns of energy we call existence. While vacuum decay paints a terrifying portrait of cosmic fragility, not all physicists see the universe as teetering on the edge of oblivion. Competing theories suggest our cosmic home might be far more resilient than the doomsday scenarios imply. Take the Higgs field stability. Some calculations indicate its metastable state could last not just billions, but trillions upon trillions of years, making the probability of decay so remote it's practically negligible. These models propose that quantum corrections we haven't yet discovered might act like hidden guardrails, preventing the field from slipping into a lower energy state. Another intriguing counterargument comes from the accelerating expansion of the universe itself. As galaxies race apart at ever-increasing speeds, space stretches so dramatically that even a vacuum decay event might struggle to propagate. Picture trying to light a fuse underwater. The expanding universe could act like an infinite ocean, diluting the destructive potential of any decay bubble before it reaches critical scale. In this scenario, regions of space would become isolated islands, with cosmic inflation acting as a natural firebreak against universal catastrophe. Then there's the possibility that our understanding of quantum fields remains incomplete. Just as relativity revolutionized Newtonian physics, undiscovered principles might govern vacuum stability in ways we can't yet imagine. Some theorists speculate about higher dimensional effects or symmetries that lock the Higgs field into place, like invisible cosmic glue holding reality's foundations firm. Others point to the cosmological constant problem, the mysterious balance keeping dark energy's expansion in check, as evidence that hidden mechanisms already maintain equilibrium on scales we're only beginning to probe. Yet these hopeful hypotheses come with caveats. The same cosmological acceleration that might contain decay also pushes the ultimate fate of the universe toward heat death, a slow, cold unraveling. And while undiscovered physics could stabilize reality, it could equally reveal new vulnerabilities. The debate often hinges on how much weight we give to anthropic reasoning, the idea that we observe a stable universe because only such a universe could produce observers. This philosophical razor suggests that while vacuum decay might be theoretically possible, the very fact we exist to ponder it implies long-term stability. Ultimately, the scientific divide reflects a deeper truth about cosmology. We're mapping the edges of known physics with incomplete data. Every new particle collision at the Large Hadron Collider, every refinement in measuring the Higgs boson's mass chips away at the uncertainty. What feels like existential peril today might tomorrow be revealed as a mathematical quirk, or conversely, the first hint of a deeper instability lurking in the quantum shadows. Until then, the universe continues its silent balancing act, neither confirming nor denying which vision of the future holds true. Vacuum decay's leap from physics equations to pop culture reveals just how deeply this existential threat resonates with our collective imagination. Science fiction often serves as a testing ground for humanity's greatest fears, and the idea of reality itself unraveling has inspired some of the most haunting narratives across books, games, and films. Take Liu Cixin's The Three-Body Problem, where vacuum decay isn't just theoretical, it becomes the ultimate doomsday weapon, with civilizations threatening to collapse the universe rather than surrender to enemies. The novel's chilling depiction aligns surprisingly well with actual physics, showing how a single desperate act could trigger cosmic annihilation. This blending of hard science with high-stakes drama makes the terror feel unnervingly plausible, transforming an abstract concept into something visceral and immediate. Video games like Deus Ex take a different approach, weaving vacuum decay into their lore as a shadowy possibility lurking behind corporate conspiracies and transhumanist conflicts. Players uncover scattered research notes and whispered theories about experiments that might destabilize spacetime itself, a slow-burn horror that creeps in through environmental storytelling rather than explosive set pieces. What makes these portrayals so effective is their grounding in real quantum field theory. Writers often consult physicists to ensure their fictional scenarios hover in that unsettling space between speculation and legitimate scientific possibility. Even superhero media has dabbled in these themes. Marvel Comics' Ultimate series featured a storyline where Galactus, the planet-devouring cosmic entity, turned out to be a harbinger of vacuum decay, an ancient survivor fleeing the collapse of his own universe. This creative twist reframed a classic villain as something far more terrifying, not just a destroyer of worlds, but a refugee from the death of physics itself. The emotional weight comes from realizing that even godlike beings might be powerless against this ultimate cosmic reset. These fictional explorations do more than entertain. They serve as conceptual gateways, making esoteric physics accessible through relatable stories. When characters grapple with the implications of vacuum decay on screen or in novels, they're standing in for the audience, voicing the same existential questions we might ask if confronted with this reality. Their dramatized struggles help us process what it would truly mean to live in a universe where the ground beneath our feet, both literal and metaphorical, might not be as solid as it appears. Interestingly, pop culture often gets one key element right that textbooks struggle to convey: the emotional dimension of such an apocalyptic scenario. Scientific papers describe vacuum decay in detached, mathematical terms, but stories force us to confront the human side. The panic of scientists realizing their equations predict doom, the political chaos as governments debate responses to an unstoppable threat, the quiet moments of people trying to find meaning in a universe with an expiration date. These narratives remind us that physics isn't just about particles and fields. It's about the fragile web of meaning we've built atop those foundations, and what happens when those foundations might crumble. The prevalence of vacuum decay in fiction also reveals something profound about our era's unique anxieties. Where past generations feared nuclear winters or asteroid impacts, our stories increasingly focus on threats that can't be seen or fought, existential risks woven into the fabric of reality itself. This shift mirrors how scientific understanding has evolved, from fearing what the universe can do to us to fearing what the universe might become. The fact that such a niche physics concept has spawned so many creative interpretations suggests we're collectively working through deeper questions about stability, impermanence, and our place in a cosmos that might be far more fragile than it appears. While these dramatizations take creative liberties, they perform an invaluable service by sparking public interest in theoretical physics. A viewer who encounters vacuum decay in a video game might later seek out legitimate science videos, creating a bridge between entertainment and education. In this way, pop culture becomes an unexpected ally to scientists, helping translate abstract theories into narratives that stick in our minds long after the credits roll or the final page turns. The next great physicist might well trace their inspiration back to a chilling fictional portrayal of reality's precarious balance, proof that sometimes the most effective way to illuminate truth is through the careful application of make-believe. When we imagine cosmic catastrophes, our minds often jump to familiar terrors: asteroids carving craters across continents, supernova bathing planets in lethal radiation, or rogue black holes swallowing solar systems whole. These threats loom large in popular culture, fueling countless disaster movies and doomsday predictions. Yet for all their destructive potential, they share one crucial limitation: their local disasters. No matter how violent, they leave the fundamental rules of reality intact, preserving the possibility of survival somewhere in the universe. Vacuum decay operates on an entirely different level, not merely destroying matter, but rewriting the operating system that allows matter to exist at all. Consider the difference between a house fire and the sudden disappearance of gravity. The fire might reduce a building to ashes, but the land beneath it remains ready for reconstruction. But if gravity vanished, bricks wouldn't fall, water wouldn't flow, and the very concept of up or down would lose meaning. Similarly, a gamma-ray burst might sterilize entire galactic sectors, yet life could theoretically persist in shielded environments or distant worlds. Vacuum decay offers no such refuge. Its expanding sphere of transformation wouldn't just kill organisms, it would erase the conditions necessary for any conceivable form of life to arise again. Atoms, chemistry, even the behavior of light would mutate beyond recognition within the affected region. This distinction reveals why vacuum decay stands alone among existential risks. Other cosmic disasters follow predictable physics, allowing for potential detection and even mitigation. Early warning systems could track incoming asteroids decades in advance. Advanced civilizations might theoretically shield against gamma radiation or harness black holes for energy, but against a light-speed reconfiguration of quantum fields. There's no bunker deep enough, no technology sophisticated enough to withstand the rewriting of reality's source code. The moment the decay front passes a given point, every defensive strategy becomes as meaningless as a fire evacuation plan written in disappearing ink. The timescales involved heighten this asymmetry. Asteroid impacts unfold over minutes, supernova over weeks or months, windows that might allow for response or adaptation. Even the heat death of the universe, often cited as cosmology's ultimate endgame, plays out across unimaginable eons. Vacuum decay operates on an entirely different clock, instantaneous transformation at the quantum level, propagating outward at the universe's speed limit. There's no gradual decline, no lingering twilight, just the universe's laws flipping like a switch from on to alien. Yet this very totality might explain why vacuum decay remains largely theoretical while other cosmic threats dominate public consciousness. Our brains evolved to recognize patterns in immediate dangers, predators, storms, rival tribes, abstract threats that offer no sensory cues, no opportunity for fight or flight, register as less viscerally real. It's the difference between fearing a visible cliff edge and worrying about the ground's potential to turn to quicks and without warning. One triggers our instinctive alarm systems, the other remains stubbornly intellectual, no matter how mathematically sound. This cognitive disconnect reveals a profound irony about human survival strategies. We've built early warning networks for near-Earth objects and developed contingency plans for supervolcanoes, threats with odds of occurring in our lifetime far lower than vacuum decay's theoretical probability over cosmic time. Our precautionary instincts focus on visible, comprehensible dangers while the most absolute peril remains largely ignored, not because it's less real, but because it defies every evolutionary heuristic we possess. Perhaps the most unsettling comparison lies in the aftermath scenarios. Post-apocalyptic fiction thrives on images of survivors rebuilding amid ruins, a testament to life's tenacity even in catastrophe's wake. But vacuum decay's aftermath wouldn't feature ruins at all. No twisted metal, no abandoned cities, not even radioactive wastelands, just different physics. A universe where the very concept of aftermath might no longer have meaning, where the components of memory and history could cease to function as before. The complete erasure of context makes this threat uniquely horrifying, not just the end of our story, but the potential dissolution of the very language in which that story was written. This cosmic perspective forces us to confront the limits of our survival strategies. For all our technological prowess, we remain bound to a fragile island of stable physics, dependent on quantum fields maintaining their current configuration. Other existential threats challenge our ability to endure. Vacuum decay challenges our assumptions about what endurance even means in an ultimately unstable universe. The silence of the night sky takes on new weight not just as a canvas for potential disasters, but as the visible manifestation of a precarious balance that makes all disasters and all recoveries possible. Dark energy, the enigmatic force stretching our universe apart at ever-increasing speeds, might hold unexpected sway over the fate of quantum fields. While we often think of dark energy and vacuum decay as separate phenomena, they could be entangled in ways we're only beginning to grasp. Imagine the universe as a rubber sheet being pulled taut in all directions, with dark energy as the invisible hand stretching it wider each moment. This relentless expansion doesn't just affect galaxies, it might also tug at the delicate balance keeping our quantum vacuum stable. The connection lies in the Higgs field's precarious position. Just as tension on a rubber sheet could make objects resting on it more likely to slide, cosmic expansion might influence how easily the Higgs field could tunnel into a lower energy state. Some models suggest dark energy's repulsive force could act as a stabilizing factor, stretching space-time so dramatically that potential decay bubbles struggle to form coherent structures. Picture trying to light a match in a hurricane. The very fabric of space might be expanding too rapidly for the spark of vacuum decay to catch. Yet other theories propose the opposite effect. If dark energy interacts directly with quantum fields, still an open question in physics, it could subtly erode the energy barriers protecting our false vacuum. Like water slowly seeping into the foundations of a dam, these interactions might weaken the structures safeguarding reality over cosmological timescales. The terrifying implication is that the accelerating universe we observe today might not just be expanding, it could be quietly destabilizing the quantum ground beneath our feet. This duality reflects one of cosmology's greatest puzzles: dark energy's true nature. Is it a constant force woven into space-time itself, as Einstein's cosmological constant suggests, or does it emerge from dynamic quantum processes that could fluctuate over time? The answer could determine whether our universe is on a slow march toward decay or safely insulated by the very expansion that seems to isolate galaxies. Recent measurements of the Hubble constant, the rate of cosmic expansion, show puzzling discrepancies that hint at undiscovered physics. Some theorists speculate these anomalies might conceal clues about dark energy's relationship to vacuum stability. The search for answers has led scientists to probe the universe's large-scale structure for fingerprints of this cosmic tug-of-war. Subtle patterns in how galaxy clusters distribute across space could reveal whether dark energy has altered the Higgs field's potential landscape over billions of years. Other teams analyze the cosmic microwave background for imprints of primordial quantum fluctuations that might predict future instability. Each dataset adds another piece to the puzzle, slowly revealing whether dark energy is the universe's silent guardian or its unwitting executioner. What makes this investigation so urgent is the potential for a feedback loop of cosmic consequences. If dark energy does accelerate vacuum decay, the process would release catastrophic amounts of energy not as explosions, but as a fundamental restructuring of physical laws. This energy could further fuel expansion, creating a runaway effect where each quantum domino toppled makes the next collapse more likely. The universe might face not a single decay event, but a cascading phase transition rippling across space-time like cracks spreading through thinning ice. Yet there's a tantalizing alternative scenario where dark energy's expansion actually protects life-bearing regions. As space stretches, areas that might have undergone decay become isolated before the transformation can spread, creating cosmic safe zones where physics remains stable. In this view, dark energy wouldn't be a destabilizing force but a cosmic immune system, quarantining dangerous quantum fluctuations before they can infect the wider universe. Our observable cosmos might owe its longevity to this delicate balance between expansion and decay. The coming decades of astrophysical observation could tip the scales in this existential debate. Next-generation telescopes like the Vera Rubin Observatory will map billions of galaxies, searching for patterns that might betray dark energy's influence on quantum fields. Meanwhile, particle colliders push deeper into Higgs boson research, testing whether its properties shift under extreme conditions mimicking the early universe. Together, these efforts might reveal whether we inhabit a cosmos delicately preserving its stability, or one unknowingly counting down to quantum catastrophe. This interplay between dark energy and vacuum stability forces us to reconsider cosmic fragility. The same force driving galaxies apart might be the thread holding reality together, or the spark that eventually consumes it. Every measurement of the universe's expansion becomes not just a study of our past, but a prophecy of physics' ultimate fate. As the night sky grows ever darker with receding stars, we're left to wonder, is the universe's accelerating flight a sign of coming collapse, or the very reason we're still here to witness it? The quantum world never sits still, not even for an instant. What we perceive as empty space is anything but empty. Beneath the apparent stillness, the universe's quantum foam churns with unimaginable energy, where particles and antiparticles flicker into existence only to vanish again in fractions of a second. These fleeting disturbances, known as quantum fluctuations, are usually harmless, like ripples on a pond that vanish without a trace. But under the right conditions, these same ripples could become the first pebbles in a cosmic avalanche, nudging the delicate balance of the quantum fields toward catastrophic change. Think of it like a game of subatomic Jenga. The universe's stability relies on countless invisible blocks staying perfectly aligned. Most of the time, quantum fluctuations are like gentle taps. They might jostle a piece here or there, but the tower remains standing. Yet with enough random jostling, or if one fluctuation happens to hit just the right spot at the right time, the entire structure could topple. In quantum terms, that toppling isn't just a collapse, it's a transformation. A single, well-placed fluctuation could tunnel through the energy barrier, keeping our false vacuum stable, creating a microscopic seed of true vacuum that then expands uncontrollably. This unpredictability is what makes vacuum decay so unnerving. Unlike other cosmic disasters, which follow the predictable laws of gravity or thermodynamics, quantum fluctuations operate on pure probability. There's no way to predict when or where the next fluctuation might occur, or whether it will be the one that sets off the chain reaction. It's the ultimate cosmic lottery, one where the grand prize is the rewriting of reality itself. What's even more mind-bending is that these fluctuations aren't rare. They're happening everywhere all the time. Every cubic centimeter of space, from the void between galaxies to the air in your lungs, is a frothing sea of virtual particles appearing and disappearing. Normally, they cancel each other out, leaving no lasting impact. But normally isn't the same as always, given enough time, and the universe has an infinite supply. Even the most improbable event becomes inevitable. Some theorists argue this could already be happening in distant corners of the cosmos. If a quantum fluctuation triggered vacuum decay in some far-off galaxy billions of years ago, the resulting bubble of new physics could be racing toward us right now at light speed. We wouldn't know until it arrived, because the warning signal would travel at the same speed as the destruction itself. The first sign of trouble would be the universe around us suddenly operating under alien rules, assuming we even remained coherent enough to notice. Yet there's a strange comfort in this chaos. The same quantum turbulence that threatens stability is also what makes the universe dynamic and creative. Without fluctuations, particles wouldn't interact, stars wouldn't ignite, and life itself might never have emerged. The delicate dance between order and chaos is what allows existence to persist at all. Vacuum decay isn't just a glitch in the system, it's a reminder of how finely tuned that system really is. Every second that passes without collapse is a testament to the universe's improbable resilience, a cosmic tightrope walk where balance holds against all odds. Still, the question lingers: how close are we to the edge? Calculations suggest the probability of a universe-ending fluctuation in any given year is astronomically low, so low that the odds of it happening in the entire lifespan of the observable universe are negligible. But negligible isn't zero, and in an infinite cosmos, even the most impossible events must happen somewhere, sometime. The quantum foam keeps bubbling, the fluctuations keep coming, and the universe keeps rolling the dice silently, relentlessly, with every passing moment. The equations physicists use to model vacuum decay paint a chillingly precise picture of apocalypse. These aren't rough sketches or vague approximations. They're razor-sharp mathematical simulations that track how a single quantum fluctuation could rewrite reality. The models reveal a bubble wall so thin it would make a soap film look bulky by comparison, yet packing enough destructive potential to unravel the universe's fundamental rules. This boundary wouldn't just separate regions of space, it would mark the absolute edge of physics as we know it, a discontinuity where matter, energy, and even causality itself would abruptly obey alien laws. What makes these simulations so unsettling is their clinical clarity. The bubble's expansion follows mathematically inevitable paths, propagating at light speed with perfect spherical symmetry. There's no turbulence, no resistance, just a perfectly smooth front of annihilation, advancing through space-time like a shadow with no object to cast it. The models suggest the transition inside would be total and instantaneous. One moment, particles interact normally. The next, they're governed by rewritten quantum rules where atoms might not hold together, where light could propagate differently, where the very concept of particle might no longer apply. Yet for all their precision, these equations float in a sea of unknowns. Without empirical data, observations of actual vacuum decay events, physicists must extrapolate from the shaky ground of theory. The simulations assume certain properties of quantum fields that might not hold true under extreme conditions. Some hidden symmetry or undiscovered particle could stabilize the vacuum in ways the math doesn't yet account for. It's like trying to predict exactly how a house of cards will collapse without knowing if invisible threads secretly brace its structure. The disconnect between mathematical certainty and observational absence creates a unique scientific tension. On one hand, the models are rigorously derived from quantum field theory, one of physics' most thoroughly tested frameworks. They're not wild speculation but logical extensions of equations that accurately predict everything from electron behavior to Higgs boson properties. Yet on the other, they describe a phenomenon so catastrophic that its very impossibility to observe directly becomes part of its definition. If vacuum decay occurred, there'd be no observers left to record it. This paradox pushes physicists to creative solutions. Some search for indirect signatures, subtle anomalies in particle behavior that might hint at underlying vacuum instability. Others run ultra-precise measurements of fundamental constants, watching for any drift that could suggest our physics is perched on a metastable ledge. A few even propose that advanced civilizations might have left cosmological warning signs encoded in the cosmic microwave background, an absurdly ambitious attempt at interstellar communication, but one that underscores how seriously some take the threat. The models also reveal surprising nuances. Not all vacuum decay scenarios lead to total annihilation. Some transitions might produce kinder physics where matter still organizes just differently. There's even speculative math suggesting conscious observers could theoretically survive inside certain types of true vacuum bubbles, though their experience of reality would be unimaginably alien. These variants don't lessen the existential risk so much as complicate it, introducing spectrums of cosmic catastrophe where some outcomes are merely universe-altering rather than universe-ending. What emerges from these equations is less a prophecy of doom than a mirror held up to our ignorance. The very fact that such extreme scenarios can emerge from otherwise solid physics highlights how much we still don't understand about quantum fields' deepest behaviors. Each simulation run is both a warning and a challenge, a mathematical dare to either prove the instability real or discover the hidden mechanisms that keep our universe safely in its current valley of reality. Until then, the numbers keep whispering their uncomfortable possibilities, reminding us that the most fundamental aspects of existence might be more fragile than we ever imagined. Could a civilization so advanced it seems godlike to us actually patch the leaks in reality itself? The notion isn't as far-fetched as it sounds. If a species mastered quantum field manipulation, they might not just observe the universe's fragility but actively reinforce it. Picture engineers on a cosmic scale, weaving invisible scaffolding through the Higgs field to shore up its metastable state, like blacksmiths reforging the fabric of existence. Theoretical constructs like negative energy or topological defects could serve as quantum duct tape, stabilizing the vacuum against decay. Some models even suggest that sufficiently advanced beings might create early warning systems, vast networks of entangled particles designed to detect vacuum fluctuations before they cascade into catastrophe. But here's the sobering counterpoint: we're likely alone in this endeavor. The staggering energy requirements and technological leaps needed for cosmic engineering place it far beyond any civilization we've observed. Fermi's paradox looms large. If intelligent life were common, why haven't we found evidence of universe-wide stabilization projects? The silence of the cosmos might imply that no one has ever reached this level, or worse, that vacuum decay is inevitable even for the most advanced beings. Yet the absence of evidence isn't evidence of absence. A truly advanced civilization might operate on scales invisible to us, their interventions subtle enough to blend into the background of physics itself. Their repairs could be indistinguishable from natural law, like an ant mistaking the steel girders of a skyscraper for part of the landscape. Or perhaps they've already failed, their attempts to stabilize the vacuum coming too late, leaving behind only echoes in the form of anomalous cosmic signals we've yet to decipher. The deeper irony is that our very speculation about such civilizations reveals how precarious our position remains. While they might theoretically harness the energy of stars to tweak quantum fields, we're still struggling to measure those fields accurately. Our particle colliders are like stone tools compared to the quantum forges such beings would wield. And until we bridge that gap, we're left with an unsettling truth. The universe's stability doesn't rely on intelligence or ingenuity, but on blind luck and the patience of quantum probability. For now, all we can do is watch and learn. Every experiment probing the Higgs boson's properties, every telescope scanning for cosmic anomalies, is a small step toward understanding whether the universe is a fixer-upper or a ticking clock. The answer might lie somewhere between the equations we've written and those we haven't yet imagined, a reminder that our grasp of physics, no matter how sophisticated, is still just a flicker in the dark. The most unsettling thing about vacuum decay isn't its destructive power, it's the silence. Picture standing on a hilltop at night, watching the horizon for storms. A supernova would paint the sky with light. A gamma-ray burst would trigger radiation alarms across the planet. Even an asteroid impact would send tremors through the ground. But vacuum decay, nothing. No warning flares, no distant rumble, not so much as a flicker in the stars. One moment, physics works as it always has, the next, it doesn't. The universe's operating system updates without a loading screen, and by the time you notice, you're already running on incompatible hardware. This absence of spectacle makes it uniquely terrifying among cosmic threats. Most disasters announce themselves with fanfare: the brilliant flash of a dying star, the gravitational waves from colliding black holes rippling through detectors. These events leave evidence, trails of data for astronomers to piece together. Vacuum decay leaves only absence. If it began in some distant galaxy tonight, the light from that region would arrive at Earth exactly as the transformation itself did, carrying no advanced warning. The first sign of trouble would be the trouble itself, an expanding sphere of new physics where familiar laws no longer apply, swallowing everything in its path without so much as a whisper. There's a cruel irony in this silence. The universe began with the loudest event imaginable, the Big Bang's explosive birth of spacetime, yet its potential end mirrors none of that drama. No grand collapse, no fiery implosion, just a quiet flicker in the quantum fields as reality's rules reconfigure. It's as if the cosmos, having shouted itself into existence, chooses to exit with a sigh. The contrast couldn't be starker, a beginning marked by unfathomable energy, an ending defined by its absence. This lack of observable evidence creates a paradox for scientists. How do you study something that, by its very nature, erases the tools needed to observe it? Traditional astronomy relies on analyzing light, gravity, and particle emissions, all of which would cease functioning as expected inside a decay bubble. Even the concept of observing breaks down when the rules of observation themselves change mid-process. It's like trying to document a power outage with a flashlight that stops working the moment the lights go out. The silence extends beyond mere absence of sound or light. It's an informational blackout. In a post-decay universe, the very language of physics might become untranslatable. The constants we use to describe reality, the speed of light, Planck's constant, the gravitational force, could take on new values or lose meaning entirely. Any record of the old universe's laws would be as useless as a map drawn in melting ice, its references dissolving as you try to read them. Yet this bleak scenario holds a strange kind of beauty. In a cosmos where most transformations are violent and loud, vacuum decay represents an almost poetic minimalism, the universe editing its own source code with the quiet efficiency of a backspace key. No debris, no aftermath, just a clean transition from one state of being to another. The stars wouldn't explode, they'd simply stop being stars, their atomic structures unraveling into whatever new configurations the revised physics allow. This silence also forces us to confront the limits of our cosmic significance. Humanity has spent millennia interpreting the universe's grand phenomena, eclipses, comets, supernova, as omens or messages. But vacuum decay offers no such narrative. It doesn't announce itself, doesn't explain itself, doesn't care whether we witness it or not. The indifference is absolute. In the face of such quiet obliteration, our stories, our sciences, even our fears become irrelevant. The universe isn't ending with malice or intent. It's just changing channels without bothering to check if anyone's still watching. Perhaps that's the most profound lesson hidden in this silent apocalypse. For all our technological prowess, we remain utterly dependent on a cosmic status quo we didn't choose and can't control. The night sky's apparent stillness isn't evidence of safety. It's the backdrop against which reality's most fundamental shifts might already be unfolding, unseen and unheard. Every second the stars shine as expected is both a reprieve and a reminder. The universe owes us no warnings, no fanfare, not even the courtesy of a final act. Long before quantum physics gave us vacuum decay, ancient civilizations wrestled with eerily similar visions of cosmic dissolution. The Hindu concept of pralaya describes cycles where the universe isn't just destroyed but unmade, returning to an undifferentiated state of pure potential. Unlike Western apocalypses full of fire and brimstone, this Eastern vision mirrors the silent totality of vacuum decay. Not merely the end of worlds, but the unraveling of the very fabric that allows worlds to exist. The parallels are uncanny. Both describe a reset button on reality itself, where form and structure dissolve into something primordial and alien. Nor is Hinduism alone in this intuition. Buddhist texts speak of kalpas, vast cosmic cycles ending in complete dissolution, while Taoist philosophy describes the Tao as an eternal void from which all things emerge and to which all must return. These aren't simple tales of destruction, they're sophisticated metaphors for impermanence on a universal scale. The Maya believed time itself moved in great loops, each ending with the gods dismantling existence before rebuilding it anew. What's striking isn't just their foresight, but their grasp of annihilation as something beyond mere physical catastrophe, a transformation so profound it redefines what existence even means. Even myths that seem superficially different share this undercurrent. The Norse Ragnarök culminates in the world tree Yggdrasil burning, only for new life to emerge from its ashes. But hidden in the poetic imagery is a subtle truth. The rules governing the next cycle might differ entirely from the old ones, much like a post-decay universe operating under rewritten physics. Meanwhile, Aboriginal Australian Dreamtime stories describe ancestral spirits singing the world into being, implying it could just as easily be sung out of existence. These narratives all dance around the same terrifying possibility, that reality isn't just fragile but temporary by design. The psychological impact of these parallels runs deep. Faced with an indifferent cosmos, ancient cultures externalized their existential dread as gods and monsters. Today, we chart Higgs boson decay channels instead of praying to Shiva the Destroyer, but the fundamental anxiety remains unchanged. What does it say about humanity that civilizations separated by millennia and continents all envisioned versions of vacuum decay long before the first quantum equation was written? Perhaps these myths reveal less about the universe's true nature and more about the limits of the human mind when confronting absolute oblivion. Yet there's a crucial distinction between ancient visions and modern physics. Mythology offered catharsis. Cataclysms were part of divine cycles, often followed by rebirth. Vacuum decay provides no such narrative comfort. Its aftermath isn't a cleansed world ready for renewal, but an unknown state where concepts like rebirth might not even apply. The old stories provided meaning in destruction. Our equations offer only uncertainty. This shift from metaphysical to mechanical explanations hasn't eased our dread. It simply stripped away the spiritual scaffolding we once used to frame it. The persistence of these themes across cultures suggests something profound about human consciousness. We seem hardwired to sense the universe's precarious balance, even when lacking the scientific vocabulary to describe it. The same instinct that had Bronze Age priests chanting to hold chaos at bay now drives physicists to scrutinize Higgs field measurements for signs of instability. Our tools have changed, but the essential question remains: are we living in a universe meant to last, or one that's merely paused between transformations? The myths got the existential stakes right, they just dressed them in different costumes. What emerges from this cross-cultural tapestry isn't just historical curiosity, but a mirror for our current predicament. Ancient civilizations used stories to domesticate their cosmic fears, turning annihilation into something with ritual and meaning. Modern science, for all its precision, leaves us staring raw probability in the face. No rituals, no rebirth, just cold equations. Yet in that vulnerability lies a strange kinship with our ancestors. They too looked at the stars and sensed the abyss. We simply measure it in electron volts rather than epic poems. The stories change, but the night sky's silent question endures. How long before the temporary becomes the eternal? The eerie silence of the cosmos takes on new meaning when viewed through the lens of vacuum decay. Fermi's famous question, "Where is everybody?" might have a horrifying answer: they're gone, erased by a quantum apocalypse they never saw coming. This idea transforms vacuum decay from a theoretical curiosity into a potential great filter, one of those rare existential threats capable of halting intelligent life universally and permanently. Imagine countless civilizations rising across the galaxy, each reaching the technological threshold to manipulate quantum fields, only to unknowingly nudge the universe toward collapse. Their greatest achievements might become their final acts, an unintended cosmic suicide switch hidden in the fabric of reality itself. What makes this hypothesis so chilling is its universality. Unlike asteroid impacts or nuclear war, which might devastate one planet while sparing others, vacuum decay doesn't discriminate. Once triggered anywhere, it expands relentlessly, leaving no refuge. A single advanced civilization's experiments could doom the entire observable universe, explaining why we see no signs of galactic empires or Dyson spheres. The stars remain silent not because life is rare, but because the universe is fundamentally hostile to longevity at technological scales. Every radio signal we've failed to detect might represent another civilization that blinked out before they could say hello. This perspective flips our understanding of cosmic evolution. We often assume intelligence is nature's crowning achievement, the universe's way of understanding itself. But what if consciousness is actually a destabilizing force, a phase transition as dangerous to cosmic order as ice cracking underfoot? The very tools that allow civilizations to explore their environment, particle colliders, energy manipulation, quantum computing, might be the same ones that push quantum fields past their tipping points. Our hunger to unlock nature's secrets could be the trigger for nature's reset button. Yet there's a counter-argument hiding in the numbers. If vacuum decay were easy to trigger, why hasn't it happened naturally over the past 13 billion years? Cosmic rays and quantum fluctuations have been stressing the Higgs field since the first stars formed, with no signs of collapse. This suggests either that decay requires extraordinarily specific conditions, perhaps only achievable through deliberate manipulation, or that the universe is far more stable than our current models predict. The absence of decay might indicate civilizations self-regulate once they understand the risks, or that the great filter lies elsewhere. The implications for humanity's future are profound. As we build more powerful particle accelerators and probe deeper into quantum realms, we might be walking a razor's edge between knowledge and catastrophe. Some theorists argue we should impose strict limits on high-energy experiments until we fully understand vacuum metastability. Others counter that such restraint would paralyze progress, leaving us vulnerable to other existential risks. It's the ultimate cosmic catch-22. The technology that could save us might also destroy us, while avoiding that technology guarantees stagnation. This dilemma reveals the dark irony of our cosmic position. We're like children playing with a mysterious control panel in a locked room, unsure which buttons bring light and which trigger self-destruct. The universe offers no manual, no warning labels, just the cold equations of physics waiting to be tested. Every experiment is both a step toward mastery and a roll of the quantum dice. Perhaps this explains the great silence not as evidence of our loneliness, but as the aftermath of countless civilizations that rolled one too many times. The vacuum decay hypothesis doesn't just answer Fermi's paradox, it transforms it into a cautionary tale written in the language of quantum fields. Those silent stars might be less a question than a warning, their emptiness screaming across the light years. Some thresholds aren't meant to be crossed. As we stand on the verge of manipulating reality at its most fundamental level, we're forced to confront an unsettling possibility that the universe's greatest filter isn't behind us in evolution's rearview mirror, but ahead, hidden in the quantum fog of our own ambition. Time travel seems like the ultimate escape hatch, a way to outrun even the most unstoppable cosmic disasters. If vacuum decay began consuming the universe at light speed, a hypothetical time machine could theoretically leap backward to safety, retreating to an era before the decay wave began. Or perhaps it could vault forward, emerging in a distant future where the transition has already stabilized into some new, survivable physics. But this desperate gambit runs headlong into one of vacuum decay's most unsettling truths. It doesn't just destroy matter, it rewrites the rulebook of reality itself. Imagine piloting a time machine away from an oncoming decay bubble, only to discover that the very concept of time operates differently in the true vacuum state. The equations governing causality might unravel mid-journey, stranding travelers in a temporal paradox where past and future no longer connect as they once did. Your vessel could emerge from its temporal leap into a reality where entropy flows backward, or where cause and effect are untethered, making navigation impossible. Even more chilling is the possibility that time itself could become granular like a film reel with missing frames, leaving no continuous path to escape through. The paradoxes multiply from there. If you traveled back in time to warn civilizations about impending decay, would that warning alter the probability of decay occurring in the first place? Quantum mechanics already blurs the line between observation and outcome at microscopic scales. Now amplify that uncertainty to cosmic proportions, where the act of fleeing a disaster might fundamentally change whether that disaster happens. Some models suggest that time travel within a metastable universe could create feedback loops like shouting into a canyon where the echoes grow louder until they trigger an avalanche. This isn't just science fiction. The math of general relativity permits closed time-like curves, loops in space-time that could, in theory, allow for time travel. But these models assume the laws of physics remain consistent. Vacuum decay throws a wrench into those calculations by introducing a variable Einstein never accounted for, a universe where the rules change mid-equation. A time machine designed under our current physics might become a death trap in the true vacuum, its mechanisms reliant on constants that no longer apply. The deeper irony, time travel might not just fail as an escape, it could accelerate the disaster. The energy required to warp spacetime could itself destabilize quantum fields, like shaking a snow globe until the delicate landscape inside collapses. Some theoretical models of wormholes and warp drives rely on exotic matter with negative energy density, precisely the kind of stress that could nudge a metastable vacuum over the edge. The very technology offering salvation could become the spark that ignites the fire. Yet there's a haunting counter-scenario where time travel and vacuum decay intertwine in unexpected ways. If multiple timelines exist, as some interpretations of quantum mechanics suggest, decay might propagate unevenly across them. A bubble could consume one version of reality while leaving adjacent branches untouched. Time travelers might then become unwitting carriers, hopping between timelines like rats fleeing a sinking ship, only to spread the infection further. The collapse wouldn't just move through space, it could fractalize across the multiverse. All these possibilities circle back to a single, unsettling realization. In a universe where physics itself is mutable, no refuge is permanent. Not distance, not time, not alternate realities. The only true sanctuary would be understanding, untangling the quantum threads that bind existence so thoroughly that decay becomes impossible. Until then, every hypothetical escape route remains a gamble with stakes higher than survival. They're bets placed on the durability of reality's deepest rules, where losing means more than death, it means becoming incompatible with the universe you once called home. Simulation theory offers a chillingly modern twist to the vacuum decay scenario. What if the universe isn't just unstable, but artificial? Picture reality as an unfathomably advanced computer program, humming along in some higher dimensional server farm. In that context, vacuum decay wouldn't be a random quantum accident. It could be the cosmic equivalent of a system crash or a deliberate shutdown command. The abrupt rewriting of physical laws mirrors how a corrupted file might glitch, its data overwritten by gibberish. Or worse, it could resemble a developer pulling the plug on an obsolete simulation, consigning entire virtual civilizations to digital oblivion with a keystroke. This idea gains traction from the eerie parallels between quantum mechanics and computing. The universe's pixelated nature at tiny scales, where particles pop in and out of existence like rendering artifacts, could suggest underlying code processing limits. Even the speed of light might function as a processing speed cap, preventing the cosmic computer from overheating. Vacuum decay in this framework becomes a catastrophic buffer overflow, where the simulation's memory allocation fails, causing fundamental rules to rewrite themselves chaotically. Philosophers like Nick Bostrom have argued that if civilizations routinely create ancestor simulations, the statistical likelihood we're in the base reality plummets. Add vacuum decay to that equation, and the simulation hypothesis transforms from playful thought experiment to existential threat model. An unstable universe might not reflect natural fragility. It could expose our reality as a beta version running on shaky hardware. The great silence across the cosmos. Perhaps other simulations were terminated for bugs or lack of resources, their celestial servers repurposed for newer, shinier universes. Yet there's a perverse comfort in this digital doomsday. Traditional vacuum decay leaves us powerless before indifferent physics, but a programmed universe implies programmers' entities who might preserve backups or implement failsafes. Some theorists speculate that advanced simulators would embed cryptographic signatures in cosmic constants, subtle clues of intentional design. Others suggest glitches like déjà vu or quantum anomalies could reveal the simulation's underlying code. If true, vacuum decay might not be an ending, but a transition, a system reboot loading a patched version of reality. The darkest version of this theory suggests we're trapped in an unrecognized Turing test. Our frantic attempts to stabilize quantum fields or outrun decay might be the simulation's true purpose, an experiment to see how intelligent life reacts to impending doom. Every particle collision in our accelerators, every telescope pointed at distant galaxies, could be feeding data to unseen observers. In this scenario, vacuum decay isn't a bugger, it's the predetermined endpoint, the simulation's final data collection event before deletion. Simulation theory doesn't just reframe vacuum decay, it inverts our relationship to it. Physics becomes software engineering, cosmology turns into reverse engineering, and existential risk transforms into system maintenance. Whether the universe is code or quantum fields, the stakes remain terrifyingly real. The pixels might be mathematical or metaphorical, but the potential for erasure is equally absolute. After all, it hardly matters whether reality crashes or collapses when the outcome is the same silence, and the infinite void where a universe once hummed. Science has always pushed boundaries, but vacuum decay presents a dilemma unlike any other. What if the very act of discovery could trigger universal annihilation? This isn't just theoretical hand-wringing. Every time particles collide at near light speeds in facilities like the Large Hadron Collider, they recreate conditions not seen since the Big Bang's first moments. Most physicists argue the risk is negligible. Nature routinely conducts far more violent experiments with cosmic rays. Yet the stakes are so incomprehensibly high that even a 1 in a trillion chance feels unnerving. Imagine a single experiment designed to unveil the universe's secrets, inadvertently becoming the catalyst for its erasure. The ethical weight of that possibility divides the scientific community into two camps: those who see restraint as irrational paranoia, and those who believe some doors shouldn't be opened, no matter how tantalizing the knowledge behind them. At the heart of this debate lies a power struggle over who gets to gamble with existence itself. Particle physicists aren't rogue actors. Their work undergoes rigorous peer review and governmental oversight. But how prepared are ethics committees or politicians to evaluate risks that transcend human scales? A nuclear accident might render continents uninhabitable, but vacuum decay wouldn't leave continents or even atoms intact. Traditional risk assessment frameworks crumble when facing scenarios where the very metrics for measuring consequences could vanish mid-calculation. This creates a chilling asymmetry. The people most qualified to assess the danger are also those most invested in proceeding, while the broader public lacks the technical literacy to weigh in meaningfully. The parallels to Prometheus stealing fire are undeniable, but with a cruel twist. Ancient myths warned of gods punishing hubris. Here, the universe itself might enforce the penalty. Some researchers advocate for a cosmic version of the precautionary principle halting certain high-energy experiments until we better understand vacuum metastability. Others counter that such hesitation would paralyze progress, leaving us vulnerable to other existential threats like asteroid impacts or runaway AI. It's a catch-22. The technology that might one day stabilize quantum fields could also destabilize them, and we won't know which path we're on until it's too late. Philosophers add another layer to this quandary by questioning whether humanity has the right to make decisions affecting all potential life in the cosmos. If vacuum decay propagates infinitely, a single lab's mistake could erase not just Earth, but galaxies teeming with undiscovered civilizations. This transforms the debate from a scientific policy discussion into a moral referendum on our species' stewardship of reality. Are we careful gardeners tending the quantum fields, or reckless children playing with matches in a cosmic tinderbox? The absence of evidence that other civilizations survived their own high-energy research offers no reassurance. It could simply mean none ever did. Yet for all the existential angst, there's a pragmatic counterargument. If the universe were so fragile, wouldn't it have collapsed already? Natural particle accelerators like quasars and colliding neutron stars have been slamming matter together at extreme energies for billions of years without triggering decay. This observational evidence suggests either that vacuum stability is more robust than theory predicts, or that the specific conditions required for collapse are so precise they've never naturally occurred and might be unreachable by human engineering. But probably safe is cold comfort when the worst-case scenario is absolute. The tension between curiosity and caution may never fully resolve. Every generation faces its own version of this dilemma, from splitting the atom to editing genes, but vacuum decay raises the stakes to metaphysical levels. Perhaps the answer lies not in halting exploration, but in directing it, prioritizing experiments that probe the Higgs field's stability margins before pursuing energies that dance closer to the edge. Like navigators charting a minefield, we'd advance carefully, mapping safe passages through the quantum landscape. But even that approach relies on an unsettling assumption that we can recognize the mines before we step on them. In a universe where the rules themselves might change without notice, that's a gamble with the highest possible stakes, one where losing means no one remains to say, "We shouldn't have done that." The universe's ultimate fate might come down to a choice between two cosmic nightmares, a slow, cold fade into nothingness, or a sudden, silent rewrite of reality itself. On one side stands heat death, the inevitable victory of entropy, where galaxies drift apart into eternal darkness, stars burn out, and even black holes evaporate over incomprehensible eons, leaving behind only a thin, lukewarm haze of particles too distant to ever interact again. It's the universe winding down like an old clock, its energy so evenly scattered that time itself loses meaning. On the other side looms vacuum decay, the quantum wildcard, a single, unstoppable wave reconfiguring the fabric of existence in an instant, replacing the familiar laws of physics with something alien and unpredictable. One scenario drags on for trillions of years, the other could happen before you finish this sentence. What makes this contrast so striking isn't just the timescales involved, but the fundamental nature of the threats. Heat death is the universe dying of old age, exhausted and stretched thin, while vacuum decay is more like a surprise heart attack. No warning, no recovery, just an abrupt transition to a state where concepts like life, matter, or even time might no longer apply. The irony is that decay, for all its violence, could be almost merciful compared to the drawn-out despair of heat death. Imagine the difference between vanishing mid-breath versus watching every star, every planet, every atom you've ever known disintegrate over epochs so vast they dwarf human history. One is a blink into oblivion, the other is an endless march toward irrelevance. Yet there's a bizarre symmetry to these twin apocalypses. Both hinge on the behavior of quantum fields, heat death emerging from the relentless increase of entropy, decay from the potential instability of the Higgs field. Both are inevitable according to our current physics, their countdowns ticking away on cosmic clocks, and both render human achievement meaningless in the grand scheme, though in radically different ways. Heat death reduces all structure and complexity to a featureless equilibrium, while vacuum decay might erase the very conditions that allow structure to exist at all. One turns the universe into a graveyard, the other into a blank slate. The real horror, or perhaps the dark humor, lies in how little control we have over which scenario wins. Heat death is a foregone conclusion if the universe remains stable, the inescapable endgame of thermodynamics. Vacuum decay, though statistically less likely in any given moment, is the wild variable, the chance that the universe could shortcut its own demise by collapsing into a new state. Some theorists even speculate that decay could already be underway in some distant galaxy, its bubble of new physics racing toward us at light speed. We wouldn't know until it arrived, turning the slow-motion tragedy of heat death into a moot point. This cosmic coin toss forces us to confront uncomfortable questions about meaning. Is it better to exist in a universe that fades slowly, giving civilizations eons to ponder their insignificance, or one that could vanish without warning? Does the possibility of a swift, total erasure make life more precious or more futile? The answers might not matter in the end, but they reveal something profound about our place in the cosmos. We're temporary inhabitants of a reality that's either on borrowed time or already expired. We just don't know which yet. The only certainty is that the universe plays by its own rules, indifferent to our hopes or fears. Whether it chooses the slow unraveling of heat death or the quantum guillotine of vacuum decay, the outcome remains the same, a reality where humanity, and everything we've ever known, becomes a footnote in a story that no one is left to read. The stars might fade, or the rules might change, but either way, the cosmos has an expiration date. Facing the possibility that reality itself could rewrite its rules without warning does something strange to the human psyche. It cracks open our usual ways of measuring meaning. On one hand, the sheer scale of the threat feels paralyzing. What's the point of building, creating, or loving if a quantum flicker could erase not just our lives, but the very laws that make those lives possible? Yet there's another, quieter revelation hidden in that fragility. If existence is this precarious, then every moment we get to experience it becomes astonishingly rare. The universe doesn't owe us permanence. The fact that we're here at all, that particles arrange themselves just so to allow consciousness to flicker awake in the cosmic dark, that's not just luck. It's a defiance. This tension between dread and wonder isn't new. Ancient Stoics practiced memento mori, remembering death to sharpen their appreciation for life. Buddhists speak of impermanence as the fundamental texture of existence, but vacuum decay twists the knife further by applying that impermanence not just to individuals or civilizations, but to reality's operating system. It's one thing to accept that you'll die. It's another to grapple with the idea that the rules governing your atoms might dissolve before your body does. Yet in that unsettling thought lies an unexpected gift, the absolute certainty that right now, in this sliver of cosmic time, the universe is holding its shape just long enough for you to witness it. The emotional whiplash makes sense. We're pattern-seeking creatures wired to expect continuity: sunrises, seasons, the dependable laws of physics. Vacuum decay shatters that illusion, revealing existence as a temporary performance on a quantum tightrope. But here's the paradox: that very instability can amplify life's intensity. Think of standing on a cliff's edge where the danger sharpens your senses until colors seem brighter, sounds clearer. Now apply that to everything: the coffee in your cup, the laughter of a friend, the weight of a book in your hands. All of it gains a luminous urgency when you realize none of it had to exist at all. This isn't just philosophical musing, it's neuroscience in action. Studies show that confronting mortality, what psychologists call terror management, can trigger two responses: paralysis or a surge of purposeful living. The same applies to cosmic mortality. Some might retreat into nihilism, arguing nothing matters if it could all vanish tomorrow. But others respond by etching meaning deeper into the present, like carving initials into a tree moments before a storm. The storm might still come, but the carving was real. What makes vacuum decay uniquely haunting is how it strips away our usual coping mechanisms. When facing personal mortality, we comfort ourselves with legacies: children, art, scientific contributions that outlive us. But against a universe-wide reset, those fade into irrelevance. The only response left is the raw, unmediated act of experiencing, not building for a future that might not arrive, but fully inhabiting the present that stubbornly persists. It's terrifying, yes, but also clarifying, like wiping fog from a mirror to finally see your own face. Perhaps that's the secret hidden in this cosmic sword of Damocles. By dangling the threat of absolute erasure, it forces us to confront what truly matters when all illusions of permanence are stripped away. Not grand monuments or eternal fame, but the quiet miracle of a universe that, against all odds, allows for moments of connection, curiosity, and awe. Vacuum decay doesn't just threaten to end the story, it reveals how extraordinary it is that there's a story being told at all. And in that revelation, even the fear becomes a kind of privilege, the privilege of being here now to feel it. Vacuum decay lingers in the back of every physicist's mind, a ghost haunting the equations, whispering that reality as we know it might be nothing more than a temporary arrangement in an endless cosmic dance. It's the ultimate reminder that the universe doesn't owe us stability. The ground beneath our feet, the stars above, even the atoms stitching us together, all of it could be rewritten in an instant, erased by a quantum whim we can't predict or prevent. Yet here's the paradox: this terrifying uncertainty is also what makes existence so breathtaking. The same fragility that could undo everything is what allows novelty, change, and life itself to flourish. Consider the odds. For over 13 billion years, against all probability, the universe has maintained this delicate equilibrium. Galaxies have spun, stars have flared and faded, and on at least one tiny world, conscious beings emerge to ponder it all. That we're here to worry about vacuum decay is itself a kind of miracle, a statistical defiance in a cosmos that could have been stillborn or sterile. The Higgs field's precarious balance isn't just a threat, it's the reason anything interesting exists at all. Too stable, and the universe might have frozen into perfect, lifeless symmetry. Too volatile, and it would have collapsed before the first stars ignited. We're left walking a razor's edge between order and chaos, where the very instability that could destroy us also created us. This duality forces a profound choice. Do we fixate on the abyss, paralyzed by what might lurk in the quantum shadows? Or do we lean into the wonder, embracing each moment as a fleeting gift in a universe that didn't have to allow moments at all? History suggests humanity's answer has always been the latter. We've built civilizations knowing they could fall to earthquakes or invasions, pursued love despite heartbreak's inevitability, and reached for the stars even as we feared the void between them. Vacuum decay is simply the ultimate expression of this existential tension, the grandest scale on which to measure our resilience. Perhaps the most surprising lesson isn't about the universe's fragility, but our own adaptability. Faced with the prospect of total erasure, we don't surrender, we get curious. Particle colliders hum, telescopes peer deeper into the dark, and equations sprawl across whiteboards as we race to understand the rules before they change. This relentless curiosity, this refusal to look away from the abyss, might be our defining trait. Whether the universe ends tomorrow or persists for trillions of years, the act of questioning it, of daring to map its contours, is what etches our brief flicker of consciousness into the cosmic record. So as the debate over vacuum decay continues, as theorists refine their models and experiments probe deeper into quantum frontiers, remember this: the universe's impermanence isn't a flaw, it's the canvas. Every painting fades, every symphony ends, but we don't dismiss their beauty because of it. We cherish them precisely because they're transient. Our cosmic moment, however long it lasts, is no different. The stars may vanish, the laws of physics may rewrite themselves, but here and now we get to witness the spectacle, and that, against all odds, is enough. If you've made it this far into the abyss with us, you're part of that defiance. Drop a like if you'd stare into the void with curiosity over dread. Subscribe for more journeys to the edge of understanding, and let us know in the comments, what would you do with a universe that might not last? The answer, whatever it is, might be the most human thing